In Chapter 17, we'll be discussing aromatic compounds. In this first video for Chapter 17, we will talk about naming benzene derivatives, the stability of benzene, aromaticity and frost circles, and the difference between aromatic versus non-aromatic versus anti-aromatic compounds. Simple compounds are benzene derivatives that contain one substituent. Now, in naming these simple compounds, benzene is going to act as the parent chain name, similar to using the longest chain name such as hexane in an alkane. The substituent is going to act as the prefix in the name. Now, I've shown two examples down here of simple compounds, and notice that I've drawn the benzene derivatives slightly different in each one. So benzene can either be drawn as a hexagon, showing the 3 pi bonds that are conjugated with one another, or, since these pi bonds are participating in resonance with one another, these pi electrons are actually rotating around all 6 carbons of the ring. So we can show that by just drawing a circle in the middle of our hexagon. So either one of these drawings is an appropriate way to draw a benzene ring. Now in our first example, we have a chlorine attached to benzene. Now the name for chlorine as a substituent is chloro. So the name of this molecule will simply be chlorobenzene. In our second example, we have an NO2 group, which is known as a nitro group. And we'll get really used to nitro groups as Chapter 17 and 18 progress. So the name of this molecule will simply be nitrobenzene. Now there are some simple benzene derivatives that are used very often in chemical labs. These are known as common compounds, and as a result, they often have alternate names that can be shorter or easier to pronounce than the typical name for a simple compound. So first, we have a methyl group attached to a benzene ring. So the proper name for this molecule is methylbenzene. However, this molecule is also known by its common name, which is toluene. And toluene is an organic solvent that's often used in labs. We also have a hydroxyl group attached to a benzene ring. This is known as hydroxybenzene. And it often goes by its common name, which is phenol. Phenol is a solid. It's very terrible smelling, but it is often used in organic labs. Next, we have a benzene ring with a carboxylic acid attached to it. Now, this is known as carboxybenzene, and this is its proper name, or its common name is benzoic acid. And benzoic acid is very useful in synthesis. And lastly, we have a benzene ring with the methoxy group attached to it. So this is methoxybenzene. Or it's known by its common name, which is anisole. And this is a liquid that is used in organic synthesis. So there are a few more common compounds that you will see in the book. These are the 4 that I would like you to know for exams and quizzes. When benzene rings contain 2 substituents, we can either indicate the positions of those substituents using numbers or special prefixes known as ortho, meta, or para. So for our first example, I will go ahead and number the carbons. Now I'm going to give bromine carbon number 1 and chlorine carbon number 2 because we want to give them the lowest possible numbers and we want to do it according to the alphabet. So bromine comes before chlorine. Now whenever 2 substituents are located right next to one another on carbons 1 and 2, it means that they are ortho to one another. So we can either write the name of this compound as 1-bromo, 2-chlorobenzene, or we can write it as O-bromo chlorobenzene. So this O means ortho, and ortho means that our two substituents are on carbons 1 and 2. Next, we have an example where the two substituents are separated by 1 carbon. So again, we can number our carbons, giving bromine carbon number 1. Now, when two groups are on carbons 1 and 3, they are meta to one another. So we can either name this molecule as 1-bromo, 3-chlorobenzene, or we can name it meta by writing in a small m, bromo, chlorobenzene. And again, this M means meta, which means the two substituents are on carbons 1 and 3. And lastly, we can have the two groups be opposite to one another on the benzene ring. So they can either be on carbons 1 and 4. Now, when they are opposite, it means that they are para to one another. So we can either have the proper name of 1-bromo, 4-chlorobenzene, or we can write it as P, bromo, chlorobenzene. And again, this P means para, which means the two groups are on carbons 1 and 4. As far as ortho, meta, and para derivatives go, it doesn't matter where you draw the substituents. As long as they are right next to each other, they will be ortho. If they are 1 carbon apart, they will be meta, and if they're on opposite sides, they will be para. So for example, we could have drawn an ortho derivative as having the bromine here, the chlorine there. We could have the chlorine there, the bromine there. Okay, so either way, this is the ortho substituted benzene ring. If we were to number the carbons, we would still follow the same rules of numbering. So we would give bromine carbon number 1. Okay, same thing for the meta position. As long as they are 1 carbon away, they will be meta to one another. So these can all represent meta-substituted benzene rings. And for para, as long as they are on opposite sides, they will be para to one another. And again, for the numbering, it will remain the same, so we're always going to give bromine number 1 since it comes first in the alphabet. And we would number in the direction to give chlorine the lowest possible number. Now, sometimes benzene is attached to a longer chain of carbons. So when benzene is actually the substituent of a larger chain, it's called a phenyl group, and that will be its substituent name. So in this example, we have a benzene ring attached to a 1, 2, 3, 4, 5, 6, 7 carbon chain. So our 7 carbon chain is going to act as the parent chain. So we'll go through the steps of naming it as we learned with naming alkanes. So we'll go ahead and number our longest chain of carbons, giving our substituent, which is the benzene ring, the lowest possible number. Then we will go ahead and name this molecule. So we have 2-phenyl. Then our longest chain is heptane. Now occasionally you will have a benzene ring attached to a carbon that's attached to a long chain of carbons. So this entire thing here is our substituent, and this is known as a benzyl group. So again, in these cases, we're going to treat the benzyl group as a substituent, and we'll go through the process of naming the molecule using our 6 carbon chain as our parent chain. So we have 1, 2, 3, 4, 5, 6 carbons. We have our benzyl group, which is the benzene ring with the CH2 attached. So we have 2-benzyl. Then our longest chain is 6 carbons, so we have hexane. And those are the two cases when benzene will be a substituent. As we're going to learn throughout this chapter and even into the next chapter, benzene is very stable. Now, even though benzene contains pi bonds, benzene is not considered an alkene. And as a result, it does not do most alkene addition reactions or oxidations that we learned in OChem 1. Now, benzene does have resonance. So this is really the 5th pattern of resonance that we learned back in chapter 2. We have conjugated pi bonds in a ring. So these pi bonds are capable of moving around the ring, and we form a resonance structure that is equivalent to our original structure. Now we can draw the hybrid structure of this molecule, which is how we get the alternate drawing of a benzene ring. So the hexagon with the circle inside, and that circle is indicating the fact that those pi bonds are moving constantly around the ring. So benzene itself is stabilized by resonance. Okay, so at no moment are these pi electrons just hanging out by themselves, ready to act as an alkene. Now, one way that we can measure the stability of compounds containing pi bonds is by using what's known as the heat of hydrogenation. Now, hydrogenation is a reaction we learned in the alkenes addition reaction chapter, and it involves hydrogen gas and a metal catalyst. And what it's going to do is add hydrogens across the pi bonds. So in this case, we're going to take our cyclic alkene and convert it into a cyclic alkane. Now, in this 6-membered ring with 1 pi bond, if we treat it with hydrogen gas and a metal catalyst, it is an exothermic reaction, and it's going to give off 120 kilojoules of energy. Now, if we take a look at a related molecule, a 6-membered ring, but now we add an extra pi bond. Well, we have 2 pi bonds that can react with 2 moles of hydrogen gas. Now, since our first pi bond gave off 120 kilojoules of energy, we would expect that 2 pi bonds would give off 240 kilojoules of energy. So that would be our expected delta H, minus 240. Now, if we were to actually perform this reaction in a lab, what you would actually observe is that this reaction gives off minus 232 kilojoules of energy. Now, this number is slightly less, and the reason that this number is slightly less is the fact that we have conjugated double bonds here. So that conjugated double bond adds a layer of stability and decreases the potential energy of this molecule. So this number is slightly less due to conjugation. Which lowers the potential energy of the molecule. Now on to benzene. Benzene has 3 pi bonds that can react with 3 moles of hydrogen gas. Now, since we saw here that we gave off 120 kilojoules of energy for 1 pi bond, we would expect that 3 would give off 360 kilojoules. However, if you were to actually measure the energy given off in this reaction, you would find that benzene actually gives off minus 208 kilojoules. So this is a huge difference. It's actually lower amount of energy given off than even the conjugated double bond that we saw in the previous example. So this big difference in energy is due to the resonance stabilization. And ultimately, this resonance for benzene is known as aromaticity. Now, benzene is an excellent and one of the most common examples of an aromatic compound, but what we're going to see in the next video is it's not the only example of an aromatic compound. But let's go ahead and take a closer look at benzene and see what makes it aromatic. So first, for a molecule to be aromatic, all atoms in the conjugated system must be sp2 hybridized. So we have our conjugated system amongst all 6 of these carbons here and these 6 pi electrons. Now each one of the carbons in this molecule is sp2 hybridized. Now this is important because atoms that are sp2 hybridized also have one unhybridized p orbital. Now in order for a compound to be aromatic, the p orbitals must overlap continuously with one another. What that means is the molecule must be a planar ring. Okay, so we have 2 pieces of criteria so far, sp2 hybridization and a planar ring. So for this one, if you were to have a long chain of sp2 hybridized carbons and pi electrons associated with them, that would simply just be a conjugated system. All of the carbons would need to be connected in a ring in order to be aromatic. And last, the molecule must follow what's known as Huckel's rule. And with Huckel's rule, it means that the molecules must contain an odd number of electron pairs. And specifically, we're talking about pi electrons. So if a molecule contains one pair, one being our odd number of pi electrons, that's equivalent to the molecule containing 2 pi electrons. It can also have 3 pairs. 3 pairs would mean a total of 6 pi electrons. It can contain 5 pairs. 5 is 10 pi electrons. So you have to have the specific number of pi electrons in order for the compound to be aromatic. Now mathematically, this number comes out to 4n plus 2 pi electrons, means that the molecule has the potential of being aromatic, where n can equal any integer. So what this is doing, this mathematical formula, is it means that you can consider every possible aromatic compound to ever exist. So if you were to insert the number 100 into this formula, 4 times 100 plus 2 would mean that a compound that has all sp2 hybridized atoms, is a planar ring, and has 402 pi electrons can be considered aromatic. So this formula is just helping us determine which numbers of pi electrons we can possibly use for an aromatic compound. So what makes benzene aromatic? Well, let's go ahead and take a look at its molecular orbitals that are involved in holding the pi electrons. Now, benzene contains 6 carbons. Each carbon has one p orbital containing 1 pi electron. Okay, so let's go ahead and indicate that with an orbital diagram. So each of these lines is representing a p orbital. And each orbital is going to hold 1 pi electron. Now these 6 p orbitals are going to combine to form 6 pi molecular orbitals. Similar to the molecular orbitals that we saw in chapter 16. Now these molecular orbitals are going to be arranged in this way. Okay, so we have a total of 6. Now half of them, and these are all in increasing energy, half of them, we'll go ahead and draw a dashed line here, half will be known as bonding molecular orbitals. Now, bonding molecular orbitals are lower in energy, and it's more favorable for the electrons to be in bonding molecular orbitals. Above the line are known as anti-bonding molecular orbitals. Now we're going to take our 6 pi electrons and distribute them in our 6 molecular orbitals, starting from the lowest energy level. Now our rules for electron filling in orbitals is we start at the lowest energy level, and we pair them up before moving up. So we'll take 2 of our pi electrons and fill them in our lowest molecular orbital. Next we move up, and we'll put 2 more by themselves, and then we'll come back and pair up the last 6. So we've taken 6 pi electrons, we've put them in our molecular orbitals, and it turns out that all of the electrons are paired in bonding molecular orbitals. None of the electrons are in anti-bonding molecular orbitals. So having all pi electrons paired in bonding molecular orbitals and none in anti-bonding MOs leads to the stability of benzene. Now let's go ahead and take a look at another example on the next slide. Now we just saw with benzene that we can explain its stability by looking at its molecular orbital diagram. But the question becomes, how do we know the arrangement of the orbitals? So how did I know to draw those 6 molecular orbitals in the way that I did that gave us 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals? Well, we're going to go ahead and learn a tool called frost circles. And frost circles will help us draw molecular orbital diagrams. And we will go ahead and draw a frost circle for this compound right here. So the first step in a frost circle is you want to draw a circle. I will go ahead and draw my circle right here. And don't worry, it doesn't have to be a perfect circle. Next, we're going to draw the polygon of the molecule with one corner at the bottom. So polygon is a shape. Benzene is a hexagon. So in the case of benzene, we would draw a hexagon inside the circle with one of the corners at the bottom. In our example, our molecule's shape is a square. So I will draw a square, and I want to make sure that one of the corners of the square is at the bottom of the circle. Next, I'm going to mark an orbital at each intersection. I'll go ahead and mark my orbitals in red. So the intersection is where the circle and the polygon interact. So we have 4 intersections here, which makes sense since we're starting with 4 pi electrons and we're going to get 4 molecular orbitals. Next, I'm going to draw a dotted line through the center of the circle and erase the circle. I will draw my dotted line in orange. Now my dotted line is going to go through 2 of those molecular orbitals. Then I'm going to fill in my pi electrons. So in my molecule, I have 4 pi electrons. So I'm going to take those 4 pi electrons, I'm going to pair up 2 of them in the lowest molecular orbital. The other 2 will go in the next highest energy molecular orbital. Now again, this is increasing energy. And anything below the dotted line is going to be a bonding molecular orbital. Anything above is going to be anti-bonding. And anything on the dotted line, such as these 2, are known as non-bonding molecular orbitals. Now in this molecule, we have 2 electrons that are paired in bonding molecular orbitals, but we also have 2 unpaired electrons in non-bonding molecular orbitals. So the fact that we have these 2 electrons in non-bonding molecular orbitals is going to decrease the stability of this compound. Now this compound is known as cyclobutadiene. And cyclobutadiene is not aromatic, and in fact it is known as anti-aromatic. So we have 3 categories for what molecules can be. They can either be aromatic, non-aromatic, or anti-aromatic. Now if they're aromatic, we have all sp2 hybridized atoms, we have a planar ring, and we have Huckel's rule number of pi electrons. Now the importance of Huckel's rule is Huckel's rule ensures that all electrons will be paired in bonding molecular orbitals. Now, non-aromatic compounds do not follow any of the criteria for aromaticity. So that means that it may contain an atom that is not sp2 hybridized. It may contain a molecule that's not a ring. And it may not be planar. So a few examples of some non-aromatic compounds can be something like this. Okay, so with this molecule, we do have a conjugated system. However, this carbon here is sp3 hybridized. Okay, so since we don't have all sp2 hybridized atoms in our ring, then it is non-aromatic. An example of something that is not a ring would just be a simple conjugated system, such as this one. So even though we have 6 pi electrons, it's not a ring. Since it's not a ring, it means the p orbitals do not overlap. Continuously. And an example of something that is not planar. So some rings have too much ring string to actually be planar. So an example would be an 8-membered ring with 8 pi electrons. It actually folds itself up into a boat formation. Okay, so this is not planar, which means the p orbitals do not have the potential of overlapping continuously. So these are all examples of non-aromatic compounds. Then for anti-aromatic compounds. With anti-aromatic compounds, we do have all sp2 hybridized atoms. We do have a planar ring, but the only thing that's wrong is we have the wrong number of pi electrons. And really what this is saying is that if we were to draw the molecular orbital diagram for an anti-aromatic compound, we would find that some pi electrons are going to be in non-bonding or anti-bonding molecular orbitals, or they won't be paired completely in bonding molecular orbitals. Okay, so we're going to use these few pieces of criteria to determine whether or not different compounds are aromatic, non-aromatic, or anti-aromatic. Now to help you draw frost circles, so just in case your circles are not perfect or the polygons are a little skewed, the book has a really nice figure that shows how the frost circles should look for the different sized rings. So all the way from 4-membered rings all the way up to 10-membered rings. So it just illustrates what the frost circle looks like and how many of those molecular orbitals are in bonding molecular orbitals, non-bonding, or anti-bonding. So really just the 4-membered rings and the 8-membered rings have molecular orbitals right on that dotted line, right in the non-bonding section. All of the other ones will have their orbitals split between the bonding and the anti-bonding molecular orbitals. So this is a really useful graphic that you can use as you're practicing your frost circles.